chemical reactions. So in a chemical reaction, this is a chemical change. We have one or more substances that are being destroyed and converted into different substances. So the chemical reaction involves a rearrangement and exchange of atoms to produce new molecules. The atoms themselves stay the same. It's like building with Legos. You take two Lego structures and you take them apart and you put them back together and you make something different. You have the same number of every type of Lego piece as when you started. Okay? Atoms don't get lost under the couch, right? So a chemical equation is a shorthand way of describing a chemical reaction. So the general idea here is that we have reactants on the left and products on the right, and there's an arrow in between. And the arrow points in the direction that stuff's happening. So the reactants react to produce the products. Okay? There's a lot of information in a chemical equation. It will often provide the states of the reactants, whether they're solid, liquid, gas, or aqueous. It will give the formulas of the reactants and products. It'll tell us the relative numbers of molecules of each of them. And then we can use this information to figure out, well, if I started with this mass of reactant, what mass of product would I get? And that sort of information is very practical. These are the states and their abbreviations. So 3 states of matter: gas, liquid, or solid. We've talked about those. And the abbreviations are just the first letter, G, L, and S. Those are written in parentheses after the compound's formula. And then we also use AQ for aqueous, meaning it's dissolved in water. It's a very common thing that happens when we do stuff dissolved in water. So those are we call them state symbols. So let's look at the combustion of methane. So methane gas burns to produce carbon dioxide gas and gaseous water. So this is a sentence describing a chemical reaction. And one thing we should learn as we go through this is that whenever something burns, it combines with oxygen. And I think we're all aware of that, just being alive, right? That how do you put something out, a fire out? Well, you could use, you could smother it with dirt or pour water on it. What does that do? It deprives the flame of oxygen. No oxygen, no flame. So anytime something's burning, one of the reactants is oxygen. So here we have the formula for methane, CH4. It's a gas. Up here it said it was a gas. It's going to react with oxygen. We should know that oxygen at room temperature is a gas. So that's O2 because it's one of the diatomic elements. And that burns to produce carbon dioxide. We've learned how to write formulas for things like that. CO2, gas, and gaseous water. Water, H2O. So there we have the formulas and the states for each of those reactants and products. But if we look at this, there's a problem. Because if we think of the atoms in terms of Lego blocks, on the left side we have 2 oxygen Lego blocks, and over here we've got 2 oxygens here and 1 over there. We have somehow created an oxygen? That can't happen. So that says there's something wrong with our chemical equation. We say it's not balanced because it's kind of like a teeter-totter. You have to have the same number of atom of each element on each side of the arrow. We also have a problem with the hydrogens. Over here on the left, there's 4 hydrogens, and on the right, there's only 2. So what happened to the other 2? Did they turn into oxygen? No, that can't happen in a chemical reaction. We say that this equation is violating the law of conservation of mass. Because if you add up the mass of the reactants and you add up the mass of the products, they're not going to be equal. So there is a problem with our equation. So we need to balance the equation. We do this by changing this coefficients, changing the number of molecules, you can't change the subscripts. So, it would be convenient, we've got too many hydrogens over here, it'd be convenient to say, well, let's just make this CH2. But that's a different compound. It's actually not a compound. We can't just change what the formulas are. So you write the correct formulas, and then to balance the equation, you do not mess with subscripts, ever. You mess with the number of each of them. So we had a problem that there was not enough oxygen on this side. There were 3 oxygens on that side. So we can't change O2, but we can say, well, what if we had 2 of these oxygen molecules? That would give us 4 oxygen atoms. And then over here, we had an issue with hydrogen, right? There were 4 hydrogens here, and there were only 2 on this side. So let's give it 2 water molecules. So 2 water molecules. Now we've got a total of 4 hydrogens and 4 hydrogens. So that's great. And let's look at the oxygen. The CO2 has 2 oxygens, and the 2 water molecules, another 2 oxygens. So now we have 4 oxygens on each side, and we have 1 carbon on each side. So if you think of these as, spherical Legos, you could take these 3 things apart and put them back together to form these things. You wouldn't need any extra parts. You wouldn't have anything left over. That's what a balanced chemical equation describes. Any questions? Yeah.
How is H2O a gas? Is water liquid?
That's an excellent question. Why is H2O a gas here? Well, for one thing, it said so in the equation. But what happens when you burn, methane is natural gas. What happens when you burn natural gas? It gets hot, right? So when this combustion occurs, the temperature goes up significantly, and at a higher temperature, the water is a gas. But that's an excellent question. So we need to learn how to balance chemical equations. So here are the steps for those of you that like lists of instructions. First, you start out by writing a skeletal equation, bare bones, right? Using the formulas for the reactants and the products. So you get the formulas down with the arrows and the pluses in between. This is called balancing by inspection, and so there's no exact perfect way to do it. There's multiple ways you can do it as long as you end up with the final answer. So these are guidelines. Balance the atoms in more complex substances first. Always balance atoms in compounds before atoms in pure elements. You want to leave the atoms that occur as free elements last. The reason for that is you're going to be adjusting things, and if you've got something like O2 that you leave to the end, when you change the coefficient on that, you don't mess up anything else. Sometimes, depending on how you do it, you can end up with fractions for coefficients. We can't have fractions in our balanced chemical equation. It should be whole number coefficients. So you need to clear the fractions multiplying by the denominator. If you don't like fractions, I'll show you how you can avoid dealing with them, and then you should always check your final answer. So guidelines for balancing equations. We'll practice. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. First thing, we need to write the formulas for the reactants and the products. So when we read this sentence, it's the reaction between silicon dioxide and, so that and is going to be plus, to produce, that's where the arrow goes, silicon carbide and. Okay, so we've got the structure hidden in that sentence. So we need silicon dioxide. What's that formula? SiO2. That's a molecular compound because silicon is not a metal. It's a semi-metal, isn't it? What do you do about the semi-metals? Well, what seems to work is, what side of the stair-step line are they on? Silicon is on the non-metal side. So we're going to name it like it was a non-metal. Okay? So silicon dioxide, we use the prefix on the oxygen to tell us how many. So solid, we're going to put S in parentheses because they told us to do that. That's not a very nice plus. Plus solid carbon. What's the formula for carbon? C. Is it C2? No. This is where you need to know those diatomic elements. There's 7 of them. If those show up by themselves, they need to be O2 or Cl2 or whatever. Carbon's not one of them. It's a molecular element. Then we have our arrow. And then we have solid silicon carbide. Now that one might be a little challenging. But looking at the elements, silicon is a semi-metal, but it's on the non-metal side, and carbon's on the non-metal side. And so this is being named as a molecular compound, but there aren't any prefixes. One of the things we can do is ask Siri. Hey Siri, what's the formula for silicon carbide?
My web search turned something up for what's the formula for silicon carbide. Have a look.
She used to tell me what it was. She would say, the formula for silicon carbide is SiC. She'd read it, right? It's SiC. I keep hoping she'll do that again, but she's been disappointing me. So it's SiC, right? Why would we come up with one of each? What do we often leave out? Ones and monos. So here, if I were asking you to name this, I would expect you to come up with silicon monocarbide, right? This is saying silicon carbide without the mono. So if there's no prefix in a molecular compound, assume one of each. I won't do that to you on an exam. That's a solid. And carbon monoxide gas. What's the formula? CO. And that's a gas. So we've got our skeleton. Now we need to make sure that we've got the same number of atoms of each element on each side. So here we've got carbon all by itself. That's one we're probably going to leave to the end. I find a lot of times if you just start with the first element, things work out pretty well. Another tip is if you start somewhere and you start fixing and balancing and then you find that you're going around in circles and changing things over and over again, just stop. Start over with a different element. Some of these equations, it's easier if you start with one element than a different element. You can't always tell which is the easiest one. So if you're going in circles, start over with something else. I'm just going to start with silicon. So what we're doing is we're looking at how many silicon atoms are on the left side of the arrow? 1. And how many are on the right side? 1. Awesome. That one's fine. How about oxygen? There's 2 on this side and only 1 on this side. So how can I make that the same? I can put 2 in front of CO. We make 2 carbon monoxides. That'll give me 2 oxygen atoms. That changed the C, the carbon, but I hadn't done anything with carbon yet. So I'm going to go on to the carbon, which I wanted to leave till last. Here I have 1 carbon, and how many on this side? 3. So I'll put a 3 in front of carbon. And now I've got 1 silicon on each side, 2 oxygens, 3 carbons. It's balanced. So if you imagine this as a teeter-totter, and these are blocks or boxes or something that weigh different amounts, you've got the same number of each kind of box on each side, and so the teeter-totter is going to balance. It's a balanced equation. Let's do another one. Combustion of gaseous ethane, a minority component of natural gas, combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So, combines with, that's our plus, to form is an arrow, and is plus. So gaseous ethane, they gave us the formula, C2H6, and they told us it was a gas, so we put G. Combines with gaseous oxygen. What's the formula for oxygen? O2. And that's a gas. When I write these out, I leave some space before the compound or element formulas so that if I need to put a coefficient, I've got some space. Forms gaseous carbon dioxide, so carbon and 2 oxygens, and gaseous water, H2O gas. And again, this is a gas because this combustion gives off heat, and so the water is going to be a vapor at that higher temperature. So here's another method that some students like. If you like it, use it. If you don't, don't. Sort of a tally method, an inventory method. So I'm going to draw a line down the middle, and I'm just going to keep track of how many atoms of each element I have on each side. This can be useful for things that get a little more complicated. So I look at what kinds of elements do I have. I've got carbon, I've got hydrogen, and I've got oxygen. So I've got carbons, hydrogens, and oxygens. And then I'm going to look at each of these compounds and identify how many atoms of that element are in there. So C2H6, how many carbon atoms? 2. How many hydrogen atoms? 6. And how many oxygens? In C2H6? None. So just nothing. And then the O2. Well, there's no carbon, no hydrogen, and 2 oxygens. In the CO2, I've got 1 carbon, 2 oxygens. 1 carbon, no hydrogens, 2 oxygens. And in the water, I've got no carbon, 2 hydrogens, and 1 oxygen. So I can look at this line and compare the numbers on this side and on that side. I've got 2 on this side and 1 on this side. So I need to make this a 2, right? So I'm going to put a 2 in front of CO2. If I have 2 CO2 molecules, that's going to double everything down here. Does that make sense? Just keeping track of what I've got. So now I've got 2 and 2. The carbons are balanced. How about my hydrogens? We've got 6 on this side and 2 on that side. How do I make 2 into a 6? Multiply by 3. There's no adding here, you got to multiply it. So I multiply, I say I've got 3 water molecules. That multiplies all the numbers underneath. So this is 6 and this is 3. Oxygen is a good one to leave to last because when I change this one, I'm not going to mess up any of the work that I already did. So let's look at oxygen. On the left I have 2. On the right I have 7. But the oxygen is coming in pairs. This is like going to the shoe store and saying, I want 7 shoes. 7 pairs of shoes? No, 7 shoes. They'll say, I'm sorry, you can't buy 7 shoes. You can buy 6 shoes or you can buy 8 shoes, right? They won't sell you 7 shoes. But you do. I call this the odd-even problem. Here we have oxygens coming in even numbers, and I need an odd number. How do you change an odd number into an even number? Times 2. If you take an odd number and multiply by 2, it becomes an even number every single time. So that's what I'm going to do. The other option is you can do fractions. and you could put 7 halves here and then clear it later. If you understand that, you don't need my help with it, so I'm not going to talk about it. So I want to multiply by 2. So what I'm going to do is I'm going to multiply everything I've done by 2. So let's maybe do a different color for this. So I'm going to put a 2 here, and that's going to make this 4 and that 12. This is the one I'm messing around with, so I'll leave that alone right now. I need to multiply this by 2, so that becomes 4. This becomes 4 and 8. And I multiply this by 2, 6. So I get 12 and 4. Now what's... No. You got to multiply correctly. It's 6. Good grief. 3 times 2 is 6. 8 plus 4. Now I've got 14 oxygens on the right side. That's a nice even number. You go to the shoe store, I want 14 shoes. They'll sell you 7 pairs of shoes, right? So that tells me I need a coefficient of 7 in front of the oxygen, because that'll give me 14 oxygen atoms. Any questions? Really comprehending what chemical equations are representing can be a challenge. So if you're struggling with this, I would recommend using gumdrops or jelly beans or Lego blocks or something, and say, okay, the red ones are going to be carbons and the black ones are going to be hydrogens or whatever, and start with a group of 2 of these and 6 of those, and give oxygen a color and 2 of those. And then try to make these things just using what you started with. And then, well, I don't have enough. So you have to add another group of these. And just play. They call those manipulatives, right? I like candy because then you can eat it when you're done. It's a reward. So, balance chemical equation using ionic compounds with polyatomic ions. So let's do this one. Write a balanced equation for the reaction between aqueous lead-2 acetate and, there's our plus, aqueous potassium chloride to form, there's our arrow, solid lead-2 chloride and aqueous potassium nitrate. Well, we need formulas, right? Our first reactant is lead-2 nitrate. What's the formula for the lead-2 ion? Pb 2+. The Roman numeral gives us the charge. What's the formula for nitrate ion? NO3-. How do you know that? You memorize it. So then we figure out how to put these two together. We need 2 nitrates with 1 of the lead-2s, so their charges add up to 0. So my first reactant is Pb NO3 2. Got the parentheses because I have 2 of that polyatomic ion. I'm told it's aqueous, so I put AQ as the state symbol. And then it says aqueous potassium chloride. Potassium's a metal, so this is an ionic compound. Potassium is K. It's K plus because it's in group 1. Chloride is a monatomic anion. It's -1 because it's in group 7. So plus KCl, aqueous. There's our arrow. Here we've got lead-2 chloride. So the lead-2 is Pb2+, and chloride is Cl-. So I need 2 chlorides with 1 lead. The charges tell me that. Nothing about the equation, it's the charges on the ions. I don't need parentheses because it's not a polyatomic ion. The state here is S for solid. And the other one, aqueous potassium, that's K+, and the nitrate NO3 minus. And that's aqueous. So any questions about how I got that? Writing formulas from chemical names. We need to balance it. Often you can just start with the first element. Here I have PB. It only shows up in one place, so I've got PB, just one of them on the left side, and over here I've got one PB. So that's okay. Polyatomic ions often remain intact in a chemical reaction. So this NO3 shows up over here as well. The nitrate ion stayed together. It didn't come apart. So I can balance polyatomic ions that stay intact as a unit. If you want to do the nitrogen and the oxygen separately, you may. It'll end up the same. But a shortcut is to look at it as a unit. So here I have 2 nitrate ions, and on the right side of the arrow, I only have 1 nitrate ion. So I need to put a 2 in front of potassium nitrate, because that'll give me 2 nitrates. Then I look at K. Here's potassium. I have 1 on the left side, and now I've got 2 on the right side. So I need to put a 2 in front of KCl. And the last thing I need to balance is the chlorine. I have 2 chlorines here, and I have 2 chlorines there. Oftentimes with ionic compounds, like ionic equations like this, it'll take care of itself at the end. Always go back and check that everything's okay. Because sometimes, if you change one thing and it changes something you already fixed, you might not notice. So always go back and look again at the end. Any questions? So a properly balanced chemical equation should have whole number coefficients, and they should be in the lowest ratio. This is 1 to 2 to 1 to 2. That can't be simplified. This would also be balanced if this was 2 and 4 and 2 and 4, right? It would be balanced, but that's not ideal. So on an exam where it asks you to balance the chemical equation, gives you multiple choice, it's possible that there could be a trick answer where the coefficients are not reduced. So much for getting into chapter 4.